Welcome everyone. So today it's my pleasure to welcome Pau Batlle, who will be talking about kernel methods being competitive for operator learning. Thank you.
Hi everyone, thanks for the invitation. My name is Pau. I'm a PhD student at Caltech, supervised by Humanawadi. Today I'm going to present about my work in kernel methods for operator learning. This is in collaboration with Matthew Darcy, who's also a PhD student at Caltech, and Bandad Hosseini at Washington, and my advisor, Humanawadi. So I'm going to start by presenting the problem of operator learning, just in its most general abstract form, then presenting our framework to approaching this problem using kernel methods, how it is actually a family of methods with increasing complexity, and how the simplest methods in this family already achieve reasonable accuracy compared to the state of the art, and in some baselines even beat the state of the art in some accuracy complexity metrics. So let me start with describing the problem. Throughout this talk, I'm going to consider two spaces of functions, U and B. U is going to be like a space of R, K input to the real line. Similarly for B, importantly, like the input domain of the functions in U and the functions in B doesn't need to be the same. And what I would call the idealized version of operator learning is having access to pairs of functions, UI and BI, where UI is in U and BI is in B, such that there exists an operator G dagger, such that G dagger of UI equals BI. We want to learn G dagger from the data. Why do I call this an idealized version? Is because in practice, we're never going to be able to have full access to the functions UI and BI. We're just going to have a discrete approximation on a computer. But for now, to plant ideas, let's forget about that and just assume that we have access to the functions and that we're going to want to learn the operator G dagger. A very typical example, and it's going to be like mostly the type of examples that I'm going to focus on this work, is the case in which G dagger arises from a PDE. Examples of that are the solution operator, in which you want to learn the map that learns the initial condition to the solution. You might also be interested in an inverse problem where a parameterized PDE is parameterized by a function, like maybe like a coefficient, and you want to learn the function that sends the coefficient to the solution. And the reason that you might want to do operator learning in that setting is because you want to build what's called a surrogate model, which is a model that is cheaper to run than traditional numerical solvers, while hopefully retaining accuracy. And of course, there's going to be a trade-off between complexity and accuracy that I'm going to explain a bit later. But the general idea is that you want something that gives as much accuracy as possible and while being cheaper. And it depends on the application, like how much complexity are you willing to trade for accuracy. So most of the past work in this kind of problem has been focused on the operator neural networks. There's two main kinds, and with all different kinds of variations. One of them is like the DeepONet, the deep operator networks, and the other one is the Fourier neural operators. And these are going to be the main benchmarks for our work. But one of the things that we want to argue is that these methods, these neural network-based methods, have not really been benchmarked against like simpler methods. So today we're going to propose like a family of kernel-based methods that present several advantages, which are simple, fast, and competitive. They're also interpretable in the sense that you can easily understand like what each part of the algorithm is doing, and they come with theoretical convergence guarantees. And we argue that these methods can be natural benchmarks for more complex methods, like both already pre-existent and like future methods, because it's very simple to implement. It's like very fast to run. And so it's like a very good benchmark for future algorithms. So let's now think about the real version of the operator learning, in which you are not given access to the full functions UI and BI, but you have measurement functions. And the way that we mathematically represent these measurement functions is by bounded linear operators. In this case, I'm going to call it phi and bar phi. And I'm going to assume that these are bounded linear operators. One of the most canonical examples is just having UI and BI on a grid. So you have the evaluation functionals of UI and BI like at a certain collocation points. But in theory, the framework goes beyond that. in the sense that you can also support like derivative measurements, local averages, any kind of like linear operators on these functions. But for most of the time, we're going to think as these as just being evaluations. So we know UI and BI on a grid. But it's important here that we don't know them everywhere because of like the discretization of computer algorithms. We will usually also think that UI is sampled from a measure. So UI BI is also sampled from a measure in which BI is just the push forward by G. And something that I'm gonna emphasize later is that learning the operator G dagger also non-trivially depends on what measure mu the data is being sampled from. And like different measures will make learning the same operator harder or simpler. So our method can be summarized in a diagram, which first includes the setup and then will include the method. But essentially, the setting that we have before can be summarized here. There's the top row corresponds to functions. We have U and B spaces of functions, and then G dagger is the map that maps from U to B. And then B are the measurement functions. Here phi maps to Rm and bar phi maps to Rn. This induces like a true finite dimensional map, F dagger, that maps Rm to Rn. And one of the key insights to our method is that if you in the U and B with RKHS norms, so if U and B are RKHS spaces of functions, you're going to be able to go up in the diagram and like optimally reconstruct U from the measurements in Rm. So this is going to be the diagram that I have below. I'm going to exactly say what I mean by optimal reconstruction. But if U and B are RKHS spaces, there's a sense in which we can actually recover, obviously not exactly because we only have finite information, but minimax optimally, we can recover a function from its measurements. So once we have these reconstructions, which are these up arrows, what we're going to do to approximate this operator G dagger is to first approximate F dagger. So this right arrow using a matrix valued kernel. And then we're going to approximate G dagger via this composition, in which if we're giving an element of U, we're first going to evaluate it on the mesh, then apply the learned F dagger, and then use the reconstruction operator in case we want an element of B. And I have to say here that this is the setup if we are evaluating in the same mesh. I'm going to generalize later to the case in which you see a mesh during training time, but then at test time you see another mesh, which is called like a mesh invariance property, which it has been of importance in the community, and particularly like people in FNO try to emphasize the importance of operator learning methods having this property. So just a quick note on optimal recovery, which again in this diagram is the inverse process of like recovering a function U from its measurements in Rm. Since we only have finite information, of course, like we'll never be able to recover the function exactly. But if you are in an RKHS, there's a very clear notion of what's the best thing we can recover. And the best function that we can recover is the minimum function, the minimum norm function that agrees with our measurements. So here, our recovery for U is going to be, which we want to be close as U, it's going to be the minimum norm function such that it agrees with our observations. And it can be proven that these maps are minimax optimal in the sense that they are optimal when this function is chosen adversarially to U, and most importantly, like we have closed form solutions via representer theorems of these elements. So these elements, these up arrows here in the diagram, are something that we can analytically derive. It's not something that we have to train for. These formulas here should be similar. They are very similar to the standard formulas in kernel regression. And in fact, just as a sanity check, when phi and bar phi are the evaluation operators, where you see U at a series of collocation points, and you see B at a series of collocation points, you just recover the standard kernel regression solutions. So essentially, you're doing like a kernel interpolation to go up. But of course, this generalizes to linear operators beyond these observations. For the right arrow, the recovery of F-dagger, we're going to use an vector valued RKHS. So again, we're trying to learn a function from Rm to Rn. So we need a matrix valued kernel that takes pairs of Rm and Rm to linear functions of Rn and Rn, in this case matrix, and that's why matrix valued kernel. And so this also, and so once we have this will also have a closed form solution. Of course, like the expensive part here is the computation of this matrix for which there has been extensive literature to avoid the n-cube complexity via low rank approximations. But in this work, we're just going to stick to like very classical, like vanilla implementations of this. So the moral of the story is that we also have a solution for F bar, which is our approximation of F dagger of the right arrow of the diagram. So now we can put everything together. Before we get into that, like going back into this diagram, now that we have learned F bar and we have the reconstruction operator and the measurement operator, we can do this composition to recover G dagger. But the situation that can happen in practice is that we have another function. We have a test function U tilde, and the U tilde is evaluated at another mesh, or maybe we have different set of measurements. It doesn't even necessarily need to be like a subset of the mesh that we have trained on. It can be like a completely different mesh. And so for this mesh, we can also consider the optimal recovery map, which we can see here in this diagram as being these diagonal arrows. And essentially, the idea is that we know our map for this part of the diagram over here, the part with U, V, Rn, and Rm. And so what we can do to find the output of the operator on U tilde is to first map to U, be an optimal recovery way. This would be this upright diagonal arrow. Then use our learned operator to go to B, and then use a measurement if in case we want to know B in a particular mesh, in a particular output mesh. And most importantly, like this composition defines an operator valued kernel. So an operator valued kernel is the generalization of a standard kernel, standard scalar valued kernel, to the case of learning functionals between function spaces. So essentially what we're proposing is, instead of defining an operator valued kernel directly, we define an operator valued kernel implicitly using the kernels of U and V and using the kernel that you're using to recover F dagger. So something that I want to emphasize here is that what I presented is a very general framework. But here in our preliminary numerical results, we're going to focus on the simplest case of that setup, in which the choice of gamma is a diagonal kernel. So gamma for each pair of inputs U and U prime outputs a matrix. And in this case, we're going to take this matrix to be diagonal. And not only diagonal, but just a kernel, like a scalar valued kernel times the identity. So this is equivalent to recover this vector valued function independently, component-wise. And even though this seems like it's a stringent assumption, we're going to see that in practice, it really speeds up and it doesn't sacrifice accuracy. Here are some reasons why we want to start with like these simple methods. First of all, a good one would be benchmarking, which is we always want to start with the simplest method first to increase complexity, to try to understand like where complexity is helping and where complexity is hurting. And this is something that is easy to do with our method. But this simple choice is like very easy to train. Of course, training here refers not to the standard like gradient descent, but just like the computation of the kernel matrices. We also observe competitive accuracy, and we also observe that it's empirically robust to the choice of hyperparameters. The hyperparameters were tuned to just one significant digit, and like further tuning didn't really affect performance, meaning that it was not really necessary to spend a lot of time hyperparameter tuning, which is good for benchmarking purposes. We can use several library software to implement this problem, for example, scikit-learn or JAX. And we also have uncertainty quantification and convergence guarantees, which I'm going to talk about later. So I'm going to go over some numerics. And something that is really important every time that one benchmarks any numerical method is understanding this cost accuracy trade-off. And here cost refers to both training cost and inference cost. Training cost is sometimes hard to measure because it includes subjective things such as how hard was a method to train, or how well did the optimizer converge. So these things are a bit hard to measure like quantitatively. But what we have instead is just like these qualitative metrics where our method like performs fast, like the training step is very fast. You don't need to learn hyperparameters to like 5 decimal points. And you can run it on a computer without GPU. But then the inference cost, like the number of floating point operations that you need to give the output for one input, this is something that can be measured more or less precisely. And we're going to see how our method performs in a reasonably high data regime. For accuracy, we're just going to use the standard relative risk, so relative loss in the space of B. We take this norm to be the L2 norm to compare with previous results in the literature. So these are the results of our experimental setup. Something that I should emphasize is that we're taking the data of results of FNO and DeepNet from previous papers. So we don't personally train these methods. We just take the data from 2 different papers. One is a low data regime paper I'm going to cite later, and one is a high data regime paper. The low data regime looks at examples at around 1,000 data points, the high data regime at around 20,000. And the low data regime is kind of benchmarks DeepNet with FNO. So we use that data to benchmark our methods as well. And we see that our method performs close to the state of the art or beats the state of the art in both in the 3 problems of the low data regime. Like even the advection problem that I'm going to present later, we get even better accuracy, and in the other ones is comparable. And in the high data regime, we observe a similar story where across different problems we perform sometimes even better than the neural network state of the art. And when not better, it's never really far off. It's like a comparable accuracy. And as I'm going to argue later, that doesn't come with a significant cost. Like even with these simpler kernel methods that don't scale well when the number of data points is really large. Let me present us a particular instance of the examples that were on that table. I'm going to talk about Darcy flow, which is an inverse problem for a PDE. So we have this PDE here, and there's, as I mentioned, there's different maps that one might be interested in. Like one can fix U of X, which is a permeability field, and try to learn the map. Sorry, you can, yeah. So there's a typo here. Like this should be a B, the solution. But one can fix U of X and map F to B, which is the solution, or you can fix F and map the permeability field to the solution, which is what we do here, which is usually considered, which is usually given the name of like an inverse problem. So what we do is sample U from a Gaussian process, and then apply a binary function. So U is going to be discontinuous, which is going to be a function that takes two values. And then we're trying to learn the solution B with F being fixed. This is an example of how this looks like in practice. We're going to have this is like the input that I was mentioning. There's only like takes only two values. And here, this is an example of the output for this particular input. And what we see in the bottom is the difference between the true output for a test example, the predicted output, and the relative error. And if we look at the accuracy, we see that the Gaussian process method performs in the similar ballpark of the state-of-the-art neural networks. Another example is Navier-Stokes, where we have a similar learning problem of mapping a forcing term F to a vorticity field W at a given time. This is from another paper. So this is the paper where they consider high data regime. And this is similarly set up, like everything is evaluated on a grid. And we have several input-output data pairs of both input and output of this operator. Here we see a similar image. This is a typical example of input and output in the training set, and in the test set, we see that at least visually, the difference between true and predicted is small, and we see like these relative errors, which if we look at the mean over training set, are of the order of 0.1%, and this is better than any neural network that was tried in the previous paper, and it beats by a significant amount like some of the neural networks. And one of the advantages that our method is that it never performs very worse than the neural network. So there's a sense of robustness here that some neural networks don't seem to have. And I want to present another specific instance of the problem because I really want to drive home the message that while setting up operator learning problems, the specific measure from which you sample from is important. Here we see the advection problem. This is a problem. It's a problem in which you're trying to learn the solution operator. So here B solves this partial differential equation, and U0 is the initial condition. And the operator that we're trying to learn is the map that sends U0 to the solution at time t equals 0.5. The way that one sets up the data for such thing is sampling U0 from a distribution, then solving the equation with a numerical method, and then obtaining B. So there's two versions of this problem that were considered in different papers. One of them will refer to it as advection 1, and the second one will refer to it as advection 2. And they differ only in how the U0s were sampled in the training set. So the operator G is exactly the same. U0 is sampled in a different way. And visually, it becomes clear that advection 2 is like a much harder problem because the way that the randomness in the initial conditions for advection 1 is set up is that there's only going to be one jump in the function. It's going to be a binary function, -1 or 1 with one jump. But advection 2 can potentially have many more jumps, meaning that you're trying to learn the operator in part of function space, which is more challenging. And we see a very drastic difference in performance, not only in our method, but also for neural network method between advection 1 and advection 2. And essentially, this is telling us that the distribution really matters in the sense that it's not only the operator that is harder or easier to learn, it's also what data distribution you're using to learn that operator. For advection 1, with our method, we achieve like very good accuracy, some orders of magnitude better than some neural networks. And this is a linear problem, so linear regression does very well. It almost achieves numerical precision error. This has to be, this is something that it's we add here as a benchmark, not necessarily because it's realistic in practice to solve linear problems, but also to understand that if this can be considered part of our method. So it's like the simplest version of our method actually recovers linear regression. So if one wants to benchmark like operator learning problems, you can start with linear regression, then go up to like matern kernels, and then you're going to have like reasonable benchmarks for you to continue training perhaps more complex methods. But as I was mentioning before, for advection 2, which is like the same operator but in a way more challenging benchmark, both the neural networks and the kernel methods struggle a bit more. Even here, our accuracy is like slightly lower than the neural network's accuracy. It's every method seems to be performing roughly equal. And an important point here is that even though this is still a linear problem, linear regression does not do as well as before. So again, the main message here is that training distribution is important in how hard the problem is, and not only the particular operator. Some other thing that I mentioned before is the complexity at inference time. So in this paper, where they introduced this cost accuracy trade-off in the context of operator learning, we have a very detailed analysis of the test error versus complexity of many neural networks, in particular like PCNet, DeepNet, ParNet, and FNO. So what we did is take their data and compute similar quantities for our linear and GP methods, and then add them to this graph to understand where are we in this diagram. So in the x-axis, you have the number of floating point operations that you need to predict one test example. And on the y-axis, the average test error, relative test error. So we see, for example, if we look at Navier-Stokes, that as we have seen, the test error is below the neural networks. And one way to reduce accuracy is to perform PCA on both input and output space. But it's a bit problem dependent whether this reduction in complexity preserves good accuracy. Like, for example, in the Navier-Stokes problem, we observed that doing PCA reduces complexity a lot while not affecting accuracy. Probably due to the operator being well described by a linear map in kernel space with a small number of eigenvalues or principal components. However, in other examples, such as the structural mechanics and the Helmholtz examples, which I have not described, we see that using PCA is actually detrimental to accuracy. So we don't observe like the same behavior across problems, and it's kind of problem-to-problem dependent whether PCA actually retains accuracy at the cost of lowering complexity. And as I mentioned earlier, it's kind of application dependent to see how much accuracy do you need, and then understanding what's the least complex method that you can get for a particular accuracy. Or the opposite, you have a fixed number of budget of floating points operator, and you're trying to minimize the test error subject to that constraint. And again, here I should mention that these kernel methods are running like there's running on 20,000 training points, and the complexity of the kernel methods, unlike neural networks, scales with the number of training point data. But here we have not used any of the techniques that try to deal with that problem, such as low rank approximations. So using that kind of techniques, we believe that could further improve like the complexity of these methods once you are in a very high data regime. And I'm going to briefly present the theoretical guarantees. I'm just going to give you the overall flavor of the kind of results that we can get without entering much into details. So as I said, U and V are, we give them an RKHS structure. So they are RKHS spaces of functions. And the first set of assumptions is assumptions for the reconstruction operators. These are standard assumptions in learning theory, where we ask that these domains are regular, the kernels are regular, and we observe more and more data points that fill the space. So the points at which we observe the function have to eventually fill the domain, because we want to avoid, we're going to try to make claims as the number of points go to infinity and the number of functions go to infinity. So there's two limits that we can get here in an operator learning problem. We can get the limit of observing more functions, and we can get the limit as observing the functions more densely. The second set of assumptions is an assumptions on the operator and the kernels. I'm not going to go over all the details, but these are essentially technical assumptions for the kernel method to have convergence. And we're currently working on a way to drop the resolution assumption. So the main result is a convergence result as both the number of functions go to infinity and the resolution at which you observe this function goes to infinity of the worst case error in a ball in function space. And I should say that if the hypothesis holds in the particular problem, so if the operator is well behaved and the kernels are well behaved and your measurements are getting denser, this kind of result is stronger than the results that you can get with neural networks, because this is a result of the particular method that we're using. So it's not only an existence result. And in neural networks, the equivalent results that you get of this is that there exists a neural network such that it achieves either convergence or is optimal with respect to some metric. But here we say that the worst case error, so the supremum of the error of G dagger, which is the operator that we have described and we have full access to, goes to 0. Another important mention here is that this is a worst case bound. It doesn't depend, it's not an average over the measure mu. Like the measure mu is something that we use for numerics, but it's not something that appears in the theory. So as a summary, we presented a simple, low-cost and competitive kernel method. It has to be understood as a family of methods of increasing complexity. It can reduce to linear regression if you make the assumptions that all the kernels are linear, but it can go up to very complicated methods, some of which we haven't really explored. Like our numerics only go until the point where the kernels are not only diagonal, but also are like a scalar kernel multiplied by the identity. So we believe that there's potential to further improve on the accuracy using the same framework, just using more complicated setup for numerics. This method comes with theoretical guarantees, and it provides a good benchmark for general operator learning tasks, because it's something that is very easy to run. With that, I'm happy to take questions. Here's a QR link to the preprint, which is out on archive as of this month.
Thank you very much. Thank you. Any questions or comments?
I have a small question.
Sure.
So I was just wondering, in your inverse problem solutions, where does the difficulty of solving the inverse problem appear in how hard it is to learn the operator?
Would you say the difficulty of solving the inverse problem, meaning like generating the data with like a numerical solver?
No, but more like some inverse problems can, for instance, be air conditioned.
Yes.
So does that appear somewhere in I don't know, like your sample complexity results for learning the operators?
Yeah, so we don't really have good examples of that. My impression is that yes, it will. So this inverse problem of Darcy flow has to be understood as like essentially the first inverse problem that you try. So it's, let's say, the first non-trivial toy example, because you know that in some sense it's well conditioned. But the more ill-conditioned your inverse problem is, like the less regular G dagger is, and so the harder it will be for you to learn the operator. I don't believe we have like an exact quantification in the sense of how many more samples it would take to learn the operator. But generally, I think our results, if you look at the technical assumption, if you look at the technical assumption of the results and the proof, it illustrates a trade-off between the regularity of the solution, so the exponent of this Sobolev space, and the convergence rate that you get. So generally, yes, the less smooth your operator is, the harder it will be to learn, and the more samples you need. But it's hard to quantify exactly unless you know where what space your operator belongs to.
Okay, thank you.